Okay, so morning everyone. How's everything going? Good. So let's begin a class. So today we're going to talk about a classic machine learning model, which is the linear regression here. So first of all, what is linear regression? So linear regression is a linear model that is able to model the correlations between our dependent variable, which is our target, and the independent variable, which is our input. And these methods have been widely applied on different domains, such as business analysis or weather report, like predicting the weather tomorrow. So one of the reasons why this model is called linear regression is that it's linear in its parameters. So we all know that for an equation, it's linear when its graphic form can be denoted as a straight line, right? So what does linear in parameter means? Any ideas?
Some kind of parameters that are straight, like a line?
Not exactly. Any other idea?
Doesn't a parameter mean there's kind of limits? So you have a range and a limit on each side?
Yeah, so how about doing an exercise here? Okay. So here I'll provide three different types of equation. Wait. X0 plus X plus 2X2. So any idea which one is linear in parameters? So this y here means our dependent variable. And this x is our input or our independent variable. And the parameter we are going to refer is this w here. It's not a range or let's say some mathematical form, let's see. So any volunteer, like which one do you think is linear in parameters? The first one? Of course. So the first one, we can see that the w here is just times an x here. So it's, of course, a straight line. Yes?
Option 3 is also linear, right?
So option 3, we can see that this w1 is actually times w2. So if we can just decode this one, it can be times. So this term is actually not linear. So this is why the reason that I'm saying this equation is actually not linear in parameters. So what about the second one? Any suggestions?
It's non-linear?
Okay, non-linear. Any different idea? Okay. So our second equation here is actually linear in parameters. So if you focus on the x here, which is our independent variable, it's actually nonlinear because we can see there is some x squared here, right? But since we are focusing on a parameter, which is the w here, we can just ignore this x and treat it as constant, which means that this one is actually linear in parameters. Any other questions? Okay. So I believe everyone has some understanding on the linear in parameters. Let's move on the mechanism of our linear regression. So linear regression is actually very straightforward. So as I just mentioned, suppose that our output or our target is y, and our input is x. The goal of our linear regression is actually to compute a set of w, which is able to derive the output, which is y, based on this input. And remember that this x and w are all vectors here. So let's give you guys a real-world example. So suppose that we are using the aforementioned weather prediction. Our goal is to predict the temperature tomorrow, so this y here should be our temperature tomorrow. And the data we have, the x, is the humidity today, the wind speed, the temperature, and the weathers. And we are going to compute a set of W for each of those attribute, weathers or humidity, and use them and use this function for obtaining our temperature tomorrow's. Yes.
Why should we take the transpose of W?
Yeah. So here we can see the shape of this x is actually k times y, right? And the shape of our W is also k times y. So if we just do matrix multiplication with this W, so WT or W transpose will be 1 times k. And this x will still be k times 1. So when we use matrix multiplication to multiply them together, we'll obtain a scalar, which is our y. So this is, the y will be a scalar, or our temperature.
Okay.
Yes. So another interesting here is that the magnitude of this W can also reflect the importance of those attributes or those independent variables on predicting our dependent variable or temperatures. So suppose that our W for, let's say, our W for temperature today will be, let's say 5. Or that for the humidity will be 0.01. And then, since the magnitude of T is much larger than WH, it means that in this case, the temperature today is more important than the humidity today for predicting the weather tomorrow. So that's all about the mechanism of this linear regression. So let's talk about, yes?
So in the equation, going back to the equation, you have a summation before W, right?
Yes.
What are we summing the whole equation against?
Oh, sorry. That's actually a typo here. So it should be, thanks for suggesting. Since we already obtained a scalar here, we don't need that summation. Yeah. So if I put a summation here, this one should not be the matrix multiplication, but just a linear inner product. Or this one should be W times x1 times plus W2 x2, something like that. Yeah, so if we represent this equation using the vector, yes?
So isn't matrix multiplication taking the transpose and multiplying, giving that result?
Yes, so if we use matrix multiplication, we can ignore that sum there and just put a transpose here. But if we represent this equation in another form, like this one, we may be using a summation here.
Okay.
Yeah. Sorry for the typo. Yes. So that's, any other questions? Okay. So in the next part, we're going to talk about how to obtain this trainable parameter, or the W here. So to obtain this W, actually we have two different types of methods. The first one is that we can obtain this W using closed form solution. Specifically, let's say our loss function is a mean square, and this y is our ground truth annotation, or the correct answer for tomorrow's weather. And this y hat is our predictions. So basically, this equation minimizes the discrepancy between these two values, right? Yes. So to use the closed form solution, we will first compute the derivative of this loss function with respect to our parameters, which is shown here. And we are going to set it as 0. Yes?
What is meant by closed form solution?
Closed form solution means that an equation can be solved using a solution that is feasible for an accepted set or a finite set. Yeah. Yes. So basically, we're going to set it as 0, and then so this basically leads to the minimization of this equation of our loss. Then we can easily derive our W, the optimal one. So in today's class, we have talked about the definition and the mechanism, as well as the training part of our linear regression. And then in the next class, we are going to continuously talk about the next method for training the parameters here, and we will also talk about other linear methods.
Okay, we'll ask just a couple of questions here.
Sure.
Okay, so under the how it works section, there's like a little symbol. It's like X symbol R.
Yes.
What does that symbol mean?
This symbol basically represents the shape as well as the attribute of this W. So here it means that it's a matrix with shape k times 1.
Okay. And what's K?
K can be any parameters or any real value. It can be 5, it can be 6, something like that, integer.
So it's how much data we have?
Yeah, it can be how much data we have. So for this X here, K represent the numbers of inputs or numbers of different attributes we have. And notice that this K is equal to this one. So it's, yes?
This is going to be on the midterm?
Yeah, so this is actually a very important part, but I'm not sure if the professor will going to give some question about this. But this is the basis. So later on, we will talk about other methods, which is actually derived or based on these techniques.